Good morning everyone. Today I am going to discuss about linear algebra. So are you now ready to listen? Okay, so let's start. So let's discuss first about the operations of matrices. Okay, so are you now ready? Okay, so let's start. The three strategies most commonly utilized to solve frameworks or matrices or lattices of condition are substitution and unexpanded lattices. So substitution and AND are basic strategies that can successfully solve for most frameworks of two conditions in some direct steps. So the strategy of increased networks requires more steps, but its application expands a greater assortment of matrices. So addition, subtraction, and increase are the essential operations on the framework. So to include or subtract networks or matrices, this must be of identical arrange. For multiplication, the number of columns within the to begin with framework breaks even with the number of columns within the moment of framework. So let's proceed to systems of equation. So substitution and elimination are less difficult strategies of tackling conditions and are utilized also much more regularly than augmented lattices or matrices in essential polynomial math. So the substitution strategy is particularly useful when one of the factors is as of now separated in one of the conditions. So the elimination strategy is useful also when the coefficient of one of the factors is the same or its negative comparables, so in all of the conditions na siya. So the essential advantage of expanded frameworks is that it can be utilized to unravel frameworks of three or more conditions in circumstances where substitution and AND are either unfeasible or incomprehensible. So in determining the solution, the another step includes utilizing rudimentary push operations such as duplicating or isolating a push by a consistent other than zero and including or subtracting lines. The objective of these operations is to change over the framework to row echelon shape, so in which the primary non-zero entry in each push may be A1. So entries over the underneath this section are all zeros, and the primary non-zero section for each push is continuously to the correct of all such sections within the columns over it. So, a special system comprises of two direct conditions that are parallel or have an interminable number of solutions. So, to understand these conditions, you include or subtract them and illuminate for the factors x and y. So, special matrices could appear challenging to begin with, but once you practice these steps, you will be able to understand or chart any comparable sort of issue. So for no solution, write the uncommon framework or matrices of conditions in a stack organized. So we were gonna to rewrite so the conditions are stacked over their comparing factors. So, gonna eliminate the variables by subtracting the bottom equation from the top equation. Okay, so the result is 0 is equal to 0 plus 4 or 0 is not equal to 4. So, this framework has no arrangement. So, if you graph equations on your paper, you'll see that the conditions are parallel lines and don't meet. Okay, so let's go to infinite solution. So we will gonna write the framework or matrices of conditions in a stack arrangement, and for multiply, we're gonna multiply the fourth condition. Okay, so gonna rewrite the conditions again in stack arrangement, and then we are going to add the conditions together, and the result is 0 is equal to 0, so which implies that both conditions are break even with to the same line. In this way, they are interminable arrangements, and this task by graphing both conditions. Okay, so we will proceed to solving matrices in addition. Okay, If you know how to add and subtract real numbers, this subject ought to truly be a breeze. So the only thing that required in a range to legally perform the operations of addition or subtraction within the world of matrices is to form beyond any doubt that the given lattices or the matrices must have the same measure or dimension. So what does it mean for a given matrix to have the same size or measurement? Okay, so we will gonna consider two frameworks, which is A and B, and these frameworks can be included if the event that the arrangement of the lattices or the matrices are break-even with. So the two frameworks or matrices have the same number of rows and columns as well. So to add two lattices, just include the corresponding sections and put this whole within the comparing position, and within the framework, a matrix can only be added to another lattices in the event that the two networks have the same measurements. Okay, so to include two frameworks, just include the comparing entries and put this whole within the comparing position within the matrix which comes about. Okay, so the greatest thing to know with lattice expansion is that the networks have the same measurements. Okay, aka they need to be the same measure. Okay, so for illustration, a 2x2 lattice can as it were be included with another 2x2 framework. So the final matrix with a measurement of 5x5 is additionally considered to be a square matrix. So since the number of columns and the number of columns are raised to, so it is important to know that for any given framework to have and reverse, it must be a square network. Okay, so I am not saying that all square matrices rather have inverses, but the primary prerequisite for a framework to have a reverse is that it must be a square matrix to begin with. Okay? Let's proceed solving matrices in subtraction this time. Subtraction of matrix is possible by subtracting the element of another matrix. So if they have the same arrangement again. So this modern matrix is the difference between the over two matrices. So the difference between two matrices is obtained by subtracting the corresponding components of the given network. So the properties of subtracting of matrices, it is a non-commutative operation. So if we reverse the order of the matrices and subtract both of them with the same order or dimensions, the result will be different. So A minus B is not equal to B minus A. So the negative of matrix A is written as negative A, such that if the addition of matrix with a negative matrix will always produce a null matrix. Okay? So let's go to the conditions for subtraction of matrices. So two matrices should be of the same order, the number of the rows and the number of the columns. So add the corresponding element of other matrices. Okay? Okay. So now let's proceed to determinants. So before we see how to use a matrix to solve a set of simultaneous equations, we learn about determinants. So a determinant is a square array of numbers that is written within a pair of vertical lines which represents a certain sum of products. So using determinants to solve systems of equations, we can solve a system of equations using determinants. But it becomes very hard for large systems. So we will only do 2x2 and 3x3 systems using determinants. So what is the use of determinant of a matrix? So they are useful for solving linear equations, capturing how linear transformation and changes volume or area, and changing variables in integrals. So furthermore, we can view determinant as a function whose input is a square matrix and whose output is a number. So now let's proceed to R cube. So in R cube, three mutually perpendicular copies of the real line intersect at their origin. So any point in the resulting space is specified by an ordered triple of real numbers. So x sub 1, x sub 2, x sub 3. So the set of all ordered triples of real numbers is called 3 space denoted to r cube. So vectors in r cube are called 3 vectors because there are 3 components, and the geometric descriptions of addition and scalar multiplication given for 2 vectors also carry over to 3 vectors as well. Okay? The familiar x minus y plane is simply the collection of all pairs x, y of real numbers. So each such pair specifies a point in the plane as follows. So first, we will gonna construct 2 copies of the real line. So one horizontal and one vertical, which intersect perpendicularly at their origin. So these are called the axes. So then, given a pair x sub 1, x sub 2, the first coordinate of x sub 1 specifies the point's horizontal displacement from the vertical axis. So while the second coordinate x sub 2 gives the vertical displacement from the horizontal axis. Okay, so the coefficient of determination r squared is used to analyze how differences in one variable can be explained by a difference in a second variable. So for example, when a person gets pregnant, has a direct relation to when they give birth. So the usefulness of r squared is its ability to find the likelihood of future events falling within the predicted outcomes. So the idea is that if more samples are added, the coefficient would show the probability of a new point falling on the line. So even if there is a strong connection between the 2 variables, determination does not prove causality. Okay, so for example, a study on birthdays may show a large number of birthdays happen within a time frame of 1 or 2 months. This does not mean that the passage of time or the change of seasons causes pregnancy. Okay? So let's proceed to r squared. So now let's proceed to linear combinations. A linear combination of 2 or more vectors is the vector gotten by including 2 or more vectors with distinctive headings or the same direction, which are multiplied by scalar values. So the over condition appears that the vector is formed when 2 times vector is added to 3 times the vector. So what is so linear about it? So if you replace all the vectors involved in the combination with a multiple of all of those vectors, you end up with a multiple of the combination as well. So this scaling property is what makes it linear. So in other words, in the event that you take a set of matrices, you multiply each of them by a scalar, and then you include together all the items, and then at that point, you get a linear combination. So note that all the matrices included in a direct combination get to have the same measurement. That is something else matrices in expansion that would not be conceivable. And then most of the times in linear algebra, we deal with linear combinations of column vectors or row vectors, and that is matrices that have only one column or only one row. So in other words, if you take a set of matrices, you multiply each of them by a scalar, and you include together all the items. In this way, you get, and at that point, you get a straight combination. So, the matrices included in a straight combination get to have the same measurement. That is something else framework expansion would not be conceivable. So, if you take a set of matrices, you multiply each of them by a scalar, and you add together all of the products. Thus, you obtain a linear combination. Okay? Okay, another thing is that involving a linear combination need to have the same dimension. Otherwise, matrix addition would not be possible. Okay? The system is consistent if the case of the lattices has at slightest one arrangements. If it is inconsistent system, there is no solution. If it is linearly independent of the matrices has precisely one arrangement, linearly dependent if the case is reliable lattices that has an infinite number of arrangements, or if the two vectors are linearly dependent if and only if they are collinear. Okay? Okay. The set of rows or columns of a matrix are spanning sets for the row and column space of the matrix. So, if it is a finite collection of vectors in a vector space, then the span of the set of all the linear combinations of the vectors. So, a subset S of a vector space V is called a spanning set for V if span S is equal to V. So, if some vector V in a vector space V is a linear combination of the vectors in a set S, then S spans V. So, if S is a spanning set of a vector space V and the W is a subspace of V, then S is a spanning set for W. A span is the result of taking all possible linear combinations of some set of vectors. This set is a basis. So, put another way, a span is an entire vector space, while a basis is in a sense that the smallest way of describing that space using some of its vectors. So, it's the set of all the linear combinations of a number of vectors. So, one vector with a scalar, no matter how much it stretches or shrinks, it always on the same line because the direction or slope is not changing. So, one vector span is a line, two vector with scalars, we then could change the slope. Okay, so the span of any set of vectors is always a valid subspace. So, this result is still just a linear combination of the vectors in the set, which means it's still contained within the span. So, therefore, the set is closed under addition. So, now, let's proceed to spanning set. Okay, so in our previous discussion, we introduced the concepts of span and linear independence, right? So, in a way, a set of vectors S is equal to V sub 1 to V sub k span a vector space V if there are enough of the right vectors in S. So while they are linearly independent rather if there are no redundancies. So we now combine the two concepts, and this says that each basis has the same number of vectors. Okay? Thus, the measurement is well defined also. The measurement of a vector space V is the number of vectors in a premise. So if there's no limited basis, we call V an infinite dimensional vector space. So, each basis for V has the same number of vectors. So, for example, the measurement of Rn is n. So, the measurement of the vector space of the polynomials in X with real coefficients having degree at most 2 in 3. Okay? So, each vector space contains a basis. So, that's a maximal linearly independent subset. Okay, so each vector in a vector space can be composed in a one-of-kind way as a limited straight combination of the components in the basis. So let's go to dimension. So we have seen that any vector space that contains at least two vectors contains infinitely many. So it is uninteresting to ask that how many vectors there are in a vector space. So however, there is still a way to measure the size of a vector space. So, for example, r squared or r cubed rather should be larger than r squared. So, we call this size the dimension of the vector space and define it as the number of vectors that are needed to form a basis. So, to show that the dimension is well defined, we need the following theorem. So, the dimension of a vector space V is the number of vectors in a basis. So, if there is no finite basis, we call V an infinite dimensional vector space. So, otherwise, we call V a finite dimensional vector space. So, we finish this discussion with some very good news. So, we have seen that to find out if a set is a basis for a vector space, we need to check for both linear independence and span. So we know that if there are not the right number of vectors in a set, then the set cannot form a basis. So that's all for today, and I hope that you've learned something from my discussion a while ago. So thank you for listening and have a great day ahead.